This is video 3 from 6.3, although I've got a theorem from 6.1. So theorem 6. It's called 6.2 here, so this is the theorem I'm talking about. Cross-partial property of the conservative vector fields, and this is just the gradients of some function. Just recall what a conservative vector field is. It has to be the gradient of some function. So in a two-dimensional, let's pick a different color here, two-dimensional, if we have our f of xy, or field of xy, equal to some vector p of xy and then q of xy, it's conservative in R2 if the partial derivatives of each are equal. So this one with partial derivative with respect to y. So first one with respect to y, and the second one with respect to x will be equal, and then that'll show us if we have a conservative field or not. If those aren't equal, then we don't. For three-dimensional, it works similarly. You'll notice that the very first equality here, the ratio equality, deals with the first two, and the rest of the other two deal with the other combinations of x, y, z. All right, so the definitions from 6.3 are below. So the first one, let F be a vector field with domain D. Vector field is independent of path, or called path independent, if our integral with respect to of C1 is the same as our integral with respect to C2 for any two paths, C1 and C2. So if I take, say we have a field that looks like this, and I take any 2 points P1, or sorry, C1, well, let's just take P1 and P2. P1 to P2, that means I can take any two paths. Say I take this first path here is C1, and then let's take another path, C2. The integrals of those are going to be the same. All right, so it doesn't matter which way we do it or how we get there, as long as we're looking at the same 2 points and they're path independent, it won't matter which path we take. And the final thing was the theorem. If F is a conservative vector field, then F is independent of path. So if this is independent of path, then we'll know we can have the possibility of a conservative vector field.